Hello, class. Here's the recorded lecture for, again, section 12.2. And we're going to show you one more test called the homogeneity test. I think the good news is it's the exact same calculation as the independence test. So you could use the same calculation, but the outcome results, again, comparison, but it'll give you a different conclusion depending on what kind of hypothesis you're going to start with. So let's walk through this one, and it'll give us a chance to do one more of these calculations by hand, i.e. using the spreadsheet as our calculator to do the E and the test statistic calculation. And so our definition is this. In our contingency table so far, we've had individuals in the table were from a single population. And for each one, the rows and columns were random. In the original one, we had 4 majors and they were all random. And also study times. And again, those categories were picked, but again, they were random. But consider the case where one of the variables are assigned. And in this case, one of the variables is not random. And you want to take that the rows represent the separate populations, and we are interested in testing the hypothesis that the distribution of each one of the columns is the same for each one of the rows. And this is what is called homogeneity. And so the book has a really good example, so I am going to do that one. This is used in the drug industry. And let me just show you when we get there our example. So again, we need to set a null and alternative hypothesis. And then we're going to perform this homogeneity test, but the method itself is exactly the same as independence. So we have to calculate expected value. We have to calculate its test statistic. We compare it to the chi-squared value in the table, and then make a conclusion about the null hypothesis. So here's a good example. And so this is taking 2 drugs, deals with heart conditions, and saying, what if we put these together? Will the 2 drugs work together, work better than each drug separately? So this is quite interesting type of calculation. So you could see the 3 drugs there, or 2 drugs. I'm not sure how to say this, but I'll give it a shot. Telmisartan and Rapapril. And these would be the 2 drugs, and they are given separately. And then the last row we have here are both drugs together. And so in our null hypothesis, it says the distribution of outcomes of fatal heart attacks, non-fatal, and no heart attacks is the same. And then the alternative is they're not the same. And you hope that you get a better performance maybe if you put both drugs together. So that's what we're going to do in the calculation. And it's the exact same calculation that we did in the last one. And so we're going to follow these 6 steps again. And so we did the null hypothesis, and alternative is always the same for that. And so now step 2 is calculate the total for each one of the rows and columns. So again, I got things ready by putting it into the spreadsheet here. And just to refresh, again, get to try this again, you just highlight that and be able to do each one of the rows. And so you copy that, and then each one of the columns. I'm sorry, these are the rows. I just did the columns. So that would be row number 1, row number 2 and 3. We just copy and paste, and we get all the totals. So how do we get the grand total? We do the sum of, say, this one here, and we got the grand total. So if we go back to, that is step 2, compute the rows and columns for each one. Now we got to calculate this crazy expected frequency. It's really an expected value calculation. And so again, the best way to do that is to set up another table here. And this would be our expected value. So what we'll do here is get rid of this and do the expected value calculation. So again, remember it's equals the row total times the column total divided by the grand total. So where's my divide? Divided by the grand total. And there you go. And so let me do a couple more. So this would be equals column total times the row total times the column total divided by the grand total. So you see, I don't have a good, way too many decimals. I need to fix the rounding a little bit. So let me do this last one here. So this last one is equals the row total times the column total divided by the total. And that should be a much bigger number than the heart attack ones, right? And so I'm going to pause the recording and finish this so you don't have to listen to all this. Okay, as you can see, I cleaned up the spreadsheet quite a bit. I actually had one typo. This, I think, said 320 and it's supposed to be 620. So I was comparing my values to what was in the book. I was off by, when you type something in wrong, there's no way to get the right answer. So these are the expected values. So let me just do one of these again, and let me just erase this one. And again, it's equals, and expected value will be the total of the row times the total of the column divided by the grand total. And you can see it's 607.14. So the next step now is to do each one of those test statistics. And just to remind everybody, let's go back to the presentation here. Let's see what step we're on here. So we're on step 4, test statistic. And so here it's O minus E squared divided by E. So again, what's nice about this is that when we set this up, we won't, we'll be able to do a copy and paste, which will be nice. So again, equal sign. So it's O, and that's the O value, minus the E value, which is that one there. And then you square it. And then again, you divide by E value. You see, you get a pretty small number, which is good. The smaller the number, the better, the larger number. Or no, I'm sorry. Anyways, it just depends. So let's copy these and get all these calculations together. So here we go. We have all these calculations. And so let me clean this up a little bit. And let's say we'll have 4 decimal points. So let me hit format and number, and let's do 4 decimals. Clean it up a little bit. There we go. So I cleaned it up a little. We do 4 decimals. So the next step is we need to add all these 9 numbers up, and that'll be our test statistic. So let's add that row up, and then we can add the other 2 rows up by copying and pasting that addition. And then the next step is to add those 3 for the total, and you get a number of 2.259. And so that's quite small test statistic compared to the last one we had, which was 35. So now we have to go back and figure out our chi number, right? Our chi-square number. And so we go back to double check here and see what we have here. Alpha level of 0.05. So we have 3 in the rows and 3 in the column. So if we go to the whiteboard here, we'll have a degrees of freedom of 3 minus 1 times 3 minus 1, right? And so that would be 2 times 2, which would be a degrees of freedom of 4. And we have our alpha level of 0.05. Let's take a look at our table. Okay, so now we're on step 5, calculate the chi-squared. So we pull up our table here, and it was 0.05, so this column right here, 4, and so we have 9.488. So if we go back to here, this is our chi, right? And this would be 9.488. So in this case, what do we have? Well, in this case, let me just show you that if you go back here, same if you use that table. So now that the test statistic is less than our chi-squared out of the table. So here we don't, instead of rejecting, we do not reject the null hypothesis. And so that's not good if you're hoping to get a better outcome with the 2 drugs compared to each single drug. But let's use the spreadsheet to calculate the p-value. So what is the p-value? So let's do this up here, p-value. And so again, we bring up that chi-squared test. And the actual is the observed, and the expected is the expected values that we calculated. And there we get a p-value of almost 70%, which is really high, right? And we're comparing it to what? 5%. And so you can see again that the value is much greater than the alpha. So again, you can't reject. So you use the term do not reject the null hypothesis. So I'm not going to lie to you, super tedious calculation, right? But if you do it in a step-by-step approach, and especially if you type all the numbers in right in your spreadsheet, once you have the formula set up, it's not too bad. But it's important to understand what you're calculating again. What you're calculating is when you get to that p-value or you compare it to a chi-squared number out of the table, it's the same thing. Where that chi-squared number out of there is implying a 5%, right? And if you calculate a p-value that's way bigger than 5%, then obviously that's where you do the do not reject. So that concept is important, and this test in particular is quite useful for the pharmaceutical industry. So that ends the recorded lecture for section 12.2, and that's it for chapter 12, which I think everybody's happy, including me.